definition, it looks like this. In fact, it looks like a ratio, which should rational, P of x over Q of x, with the exception, of course, you cannot let that denominator be 0. And we sort of glanced at these, I think, right, on Monday? We sort of glanced at it. Now, did I get a chance on Monday? I can't recall. Did I actually sketch one for you guys? Did we go through at least one problem and sketch it? And I saw some looks on faces like, what? How can I do one of these myself on that exam April 23rd? So I'm going to do this. Alexander, since you're right there near, I gave, I think, 4 examples at the bottom of the page. Did I do maybe one of those?
Yes.
I did.
You did the first one.
I did the first one. Okay, here goes. We're going to try number 2. Read number 2 and tell me what that ratio rational function looks like, and then we're going to try to sketch it.
It's 3x squared minus 3x.
Okay, now hang on. R of x is equal to 3x squared minus 3x?
Yes.
Okay.
Over x squared plus x minus 12.
There you go. Guys, please, 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 in the time we have here, these things are heavy. Now she's going to read those steps for me, and I'm going to try step by step to see what's going on here. What's step number 1 asking me to do?
To find the domain of the function.
Now, I would think, step 1, they want you to list the domain immediately for this. I don't think we could actually list the domain until this thing's cleaned up a little bit. So let's clean it up first. Guys, on top, I could factor out a 3x, a common factor. And I think I have that, if you guys agree. And the x squared plus x subtract 12, I think that will factor into what? X plus 4, x subtract 3. Let me step back and look at it. You guys agree with that? Yes or no?
Yes.
Now, please tell me now, based on everything we've done with domain in this class, what on earth can x not be?
-4.
That's all they want. -4, +3, and that's partial credit right there. Now, what's step 2 asking?
Simplify, write the function in lowest terms.
Beautiful. Hang on just 1 second. I'm going to go ahead and rewrite. We've already done it. 3x over x, 3x times x subtract 1 over x plus 4 times x subtract 3. That's all they want. We've already done it early on. The simplified version. How about step 3?
Name the intercepts of the graph.
Okay, here we go. So they want the x-intercepts on this guy's and the y-intercepts. The y-intercept on one here. On that. Guys, to find an x-intercept, always do what? Set the function equal to 0. So if I go back, if I set this r of x equal to 0, it looks like this. And we have this. Make sure you guys can see the board here. And then I'm going to go to the side here and do something with this to clean it up a little bit. Guys, if I do a quick cross multiplication or multiply both sides by x squared plus x subtract 12, please guys, will that take me to this, which would be a big help? Yes or no? Will that just take me to 3x squared subtract 3x is equal to 0? Is that true? From here to here. And then factor, which I think we factored up there earlier, which is okay. Split this up. We know the 0 product property. You end up with x is equal to 0 and x is equal to 1. And since I intend to graph, let's write these as nice ordered pairs. You get partial credit for all this. Just one problem. I just have one on the test for April 23rd because they're lengthy. One problem could be 12 points, 15 points, just one problem, because you have all this partial credit. Those are the x-intercepts. Y-intercept, well, the easier, you find r of 0. You go back up and replace all the x's by 0. Guys, if I do, of course, we end up with 0, which we sort of thought should happen, and you end up with 0, 0. All partial credit. Number 4. Get out of your way here and put that up here. Alexander, what's number 4?
Determine the vertical asymptotes, if any, of the graph.
Now hang on just 1 second before you read more, because I'm sure I put something else there. Guys, did I discuss vertical asymptotes? Those lines that the graph may approach. And I'm going to say initial here. We're looking for vertical asymptotes. Now I think on the handout I told you a good way to find where they are. What was that at the end?
Set the denominator equal to 0.
Beautiful. You go back and set this denominator equal to 0, which would be better to set this equal to 0. You're going to set x plus 4 times x subtract 3 is equal to 0. Split this up. You end up with x is equal to a negative 4 and x is equal to 3. And those are my locations for my 2 vertical asymptotes when I finally get to them. Alex, what was that question?
Will the vertical asymptotes always be the same as the domain?
Oh, tell me again.
Will the vertical asymptotes, will it always be the same as the domain?
Ah, beautiful. No, there's a case coming up where it's not. Okay, good question, though. Now I know where those vertical lines go when I finally get to the grid to graph this. Now, number 5. Oh, boy. What's number 5 asking, Alexander?
Determine the horizontal asymptote.
Guys, there's also something called a horizontal asymptote. Let me go ahead and spell that for you. In graphing these strange functions, rational functions. So there's also a line, horizontal line that my graph also will approach as I graph it. I may not touch it, sometimes it may touch it. You will never touch these. Now, did I give, oh boy, I think I gave a lengthy calculus procedure on this one. I think. Alexander, read what's with that.
To find the horizontal asymptote, we will use the end behavior of r of x equals 1 over x.
Hang on now. So they're saying refer back to this, which I think I did on Monday. This is the most simple rational function ever. They call it the reciprocal function. And guys, please remind me, did we not say that this graph looks something like this? For a quick sketch. Is that true? Now, is there a horizontal asymptote involved on this simple one? Yeah, the x-axis. My blue branches are approaching, not supposed to touch, in this case, not touching the horizontal asymptote. Now, I'd like to know on this graph, when I finally get to a graph of this function, where is my horizontal located on this one? And she says refer back to 1 over x. Now, I think I did a little bit of this on Monday. Guys, the calc technique is to go back to the original function, examine the numerator, examine the denominator, and tell me the highest exponent you see. All together. Top, bottom. What's the highest? Is x squared. I don't see an x cubed, I don't see an x to the 4th, x squared. After you discover what the highest is, they want you to divide everything by x squared for a reason. It's going to look a little strange here, but the little procedure here. Go back to the original, divide through by x squared on this one. And here. And here. And then clean that up. So the first step is to do that division. Now guys, when I say cleaned up, do a little algebra here. This turns into merely 3. Those x squareds cancel. From algebra, that second term could be renamed as 3 over x. I'll leave it like that for right now. From algebra, denominator, x squared over x squared is 1. Second term, x over x squared, do a little canceling, it's 1 over x. Now the last one's a little strange. 12 over x squared, you say, Professor, I can't do anything with that, but for the sake of what I need to do, I could rewrite it as 12 times 1 over x times 1 over x. Trying to get that 1 over x reference back in there as much as possible. Now let me go back to the top. I've got 3 over x. Guys, could I also rewrite that last term 3 over x and get the 1 over x in there some way that I need? Could I rewrite this at this moment as 3 times 1 over x? Is that still 3 over x? Okay. Now what am I allowed to do based on this graph? The limit as x gets large of this function, 1 over x, is 0. In other words, on the x-axis, as you go this way forever, as x approaching infinity, and you pull that blue graph along with you, is my blue graph getting closer and closer and closer to the x-axis, which is 0. Now, is it doing the same thing on the other end? It's like in behavior. Limit as x is approaching negative infinity for this function. So this time you're going to walk this way forever, pull the blue graph along with you, and I know it's underneath here, but what's that blue graph doing as you pull it along with you?
0.
Is it also approaching 0 from underneath, which is fine, it's still approaching 0. That gives us now, and this, we have established that each one of these, look at this, in my little technique here, each one of these, based on this, can be replaced by 0. Which helps. It's all based on that 1 over x. What 1 over x is doing. What's 1 over x doing? I have 1 over x incorporated here. Guys, that means now I have 3, of course, out front. Please tell me, if I replace 1 over x by 0, is 3 times 0 0? That's gone. I don't have to worry about it. And my denominator, I've got 1 out front, of course. My second term is 0 altogether, 1 over x. And then I got 0 here on the end times 12. Is that still 0? So are these two terms going to collapse? Gone. Leaves me a 1. And I'm left with altogether 3. Everything else is gone. Making sense? If you refer back to 1 over x. Now, before I establish that, I had some good students in this class. Saw a couple of professors before I came to class, and they were all down about some of the tests they're scoring. And professors get down. They said they had some bad scores on their calc test. Whew. I don't want that to happen to me. I don't want any bad scores. Now, some of my students have had some experience with this. Does anyone recall, I like this calculus technique, but does anyone recall a faster way to establish that my horizontal asymptote, when I get to the grid, is going to be up at 3? Besides what I just did to get 3. And some students, I'm sure, have had some experience with this and say, Professor, I saw a shortcut somewhere to get that 3 within seconds. Okay, Kim, what did you see?
When we look at the degree of the numerator.
Okay, now if the degree of the numerator, which is 2, that's highest, excellent, is a 2 degree. And if you check out the denominator, is it also 2 there? Do they match up? If they match up, Kim, help me out.
The horizontal line will be the ratio of the leading coefficient.
She said that perfectly. If they match up, it's always going to be this number, a ratio over this number. 3 over 1. If they match up as she perfectly described this. Kim, thank you. Now, I went through and showed the calculus behind it. I sort of prefer that myself, but I see a little shortcut there. Now, I know some of my students are thinking, Professor, suppose they do not match up. Suppose the degrees are not the same. And you can't use Kim's theorem on this. Then that's a different issue that we have to see later in another rational function. This one's fine. So guys, if this were x cubed, it's still 3. X to the fourth, still 3. If the degrees match up. I did this just to make sure. So guys, we'll name this as y is equal to 3. That's my location of my horizontal asymptote. Now, Alexandra, help me out. Kim's help me out. did I have anything else there under the horizontal asymptote to worry about?
Yes,
What did it say?
it's possible for the graph to intersect or cross its horizontal asymptote.
Tell me, before I get to the grid. If we have a vertical asymptote here, a vertical asymptote here, and all of a sudden you have now, today, you have a horizontal asymptote up at 3, and I'll start sketching. And I'll show you all this sketching here shortly on this particular problem here. Guys, can my sketch, and someone give me a good rationale, can my sketch, when I start sketching, can I have my graph to touch or cross one of those vertical lines? You can never touch one of the verticals. Why? What's the rationale why?
Because it's undefined at that point.
Yeah, we already said, what, you're down here in my what? Denominator? We already said what, in that domain, some student mentioned my domain here. X cannot be a what, -4 or a +3? Right? And that's the location of my vertical asymptotes when I get to the grid. You can't touch those. It says X cannot be those. Now though, the horizontal, you can touch at times. Not all the time, I'm going to show you when and where. The graph may do something like this. And follow underneath. Still not touch this. Still not touch the vertical, but could cross over and follow the horizontal underneath. Or it could stay above it, still follow it, but still not touch this vertical, never touch the vertical, but still follow the horizontal, but stay on top and follow it. So it could cross over sometimes. Woo! It's called a crossover point. Did I give a little technique on how to find that crossover point if there is one?
I don't think so.
I don't think I did. I don't think I did. So I think I'm leaving it up to you guys to help me. Tell me what the next step is, because I think that's the last step I need on this one.
It's about the oblique
Oh, yeah, no oblique on this one yet. We're not worried about oblique yet. So guys, I have enough information here. Now, someone please tell me in this class, will this happen? Will my graph somewhere cross over the horizontal, never touch the vertical? And how would you describe to me a procedure on how to find, if it does, where it doesn't cross over? So I'm looking for a crossover point on the horizontal, if possible. So is there a crossover point? And can someone tell me, if so, how would you attempt to find it? Now I've got a clever class in here. Oh, I see hands going up. Bella.
So the function equal to 3?
She said, if they have something in common, Professor, your function and that 3, that horizontal asymptote, they should be equal to one another. Right? That's where they cross over. So she says, Bella says to Professor, set 3, right here, equal to the function itself, back here. Bella, thank you so much. Here we go. You set the asymptote, horizontal, equal to the original function. That, in a sense, says, do they have something in common? If they do, that's going to be a crossover. They have that point in common. And she says, fine, it just sets the 2 equal. Now you've got to solve this. I would suggest, it's up to you, I'm going to set this up for a cross multiplication. But it's entirely up to you. I'm going to cross multiply guys like that. 3 times the x squared plus x subtract 12 will give me 3x squared. This is a nice problem. Plus 3x subtract 36. In the other direction, by cross multiplication, 3x squared subtract 3x. Or you guys may do it a little differently. Solve this, the 3x squareds will cancel. I could move this over from algebra and make this 6x. Move that 36 over, 36. Oh, look at this. There's an answer. X is 6. Avery, what do you think that X equals 6 tells me? Just out of curiosity.
That's what it crosses over.
Absolutely. So what could I write as a good solid point to show the precise point that my graph should cross over that horizontal asymptote? I know X is 6. What's my point altogether?
3.
Yeah, Y is 3. There's your point. And they call that a crossover point. Now, if you go through this routine, who was it telling me to set the two equal? Who was it? Who told me? Bella. Bella told me to do this. Now, I did it. Bella and class, if this should have happened, suppose I did what she says, and I did my cross multiplication, or try to solve this, and I got something crazy down here. I maybe got, hang on just one second. Maybe that came out to be a positive. Guys, don't change this on your notes here. Suppose that had come out to be a positive. What would happen then? The 3x squareds cancel. What's going to happen now if that had been a positive? Will also the 3x's cancel? What are you going to end up with? All the x's are gone. What might that tell you? If that should, there is no crossover point. They will not cross over. You attempted, but all your x's all of a sudden are gone. They canceled out. So that puts you on the alert. There's no crossover point. Thank goodness this one has one. Okay. Wow. Look at the board space it took me. One problem. Now we just do one more tonight. Then we'll start chapter 4. In the little time I have. Guys, any concerns here? Now on your handout, I'm having Alexandra to stop at the next step 5, I think it is, where it starts what? Oblique? You say, Professor, is there another type of asymptote besides vertical, horizontal? Look at this. I'm not going to do one tonight. You may get to the grid, and all of a sudden, for some reason, you have an oblique line. That's not the graph, that's an asymptote. And your graph must follow that in some way or the other. I don't know exactly in this case what it could do. It could do something like this, where one part follows that line. It could do something like this, where this might be a vertical, but this thing over here, the oblique, my other side's following the oblique. That could happen. And I have to show you later on how to find when and where is that. Okay? Now, with all this done, Alexandra, thank you for helping me out here. Guys, let's put all this together and see what the graph finally looks like. Then I got tons of questions here. Here we go. Guys, do label your axes. I know some students are labeling, some do not. Okay. Now, here we go. You say, Professor, where should I start? Well, we found the x and y intercepts here, if you want to plot those now. 0, 0 was the y-intercept, 0, 0, 1, 0. Okay, here we go. So we got a point here at 0. We have another one at 1. I think that takes care of the intercepts, yes or no? True? We now also have to place on the grid these. So there's a vertical asymptote out at -4. Alexander, remind the class how we found those vertical asymptotes. What was that description?
We set the denominator equal to 0.
There you go. That's all you do. Set the denominator equal to 0. And the other one was 3. So guys, when you put those on there, I like to put my vertical asymptotes for a reason in red. Just to show, I don't know for the color red, just says stay away from it. Okay, so I cannot touch these. Vertical asymptote at -4. And there's one over here at 3. Got those out of the way. Horizontal, oh, we discovered one there. It's up at 3. Put that in blue. And we'll do this. I think I'll put a solid line here for this one. It looks like this. So far, so good? Let me extend my red vertical. I think something's going to happen up there here shortly, maybe, just to make sure I get ready for it. Okay. Am I leaving anything out? Oh, there's a crossover point. What, 6-3? So out 6, up 3. We're going to plot that, extend this out. Hopefully make this look right. That was that 6. This extends on out. I'm going to go ahead and mark that. Mark that in green. Out 6, up 3, guys. Is that right here? Based on what you see. That's my crossover point. Okay, do this. Show this good forever. Okay. Now, I think I've used everything I have. Is that true? I'm ready to graph it. Now you say, Professor, do I need to plot points? Sometimes. Sometimes, though, based on what you see with the asymptotes and so forth, you can sort of have an idea what's going on. So guys, let's go from left to right. First, how many pieces to this disconnected, discontinuous function are there? Well, there's something going on to the left of this. So that's one piece. Something going on in between. Now, I don't know what's going on in between yet. In between these two. And there's something going on out here. So this thing's going to have 3 pieces to it. And they're all going to be disconnected. Let's start on the left. Any ideas? What's going on out here, and you have no point out here to work with. But you got to follow those asymptotes. So should I plot a point out there to see where that point may fall? And that may give me an idea of where my piece of my graph is located. Who has an idea? Anyone? I'll try to graph this thing further. Out to the left. Something's going on. Where is it? What does it look like? Give me an idea. We met, plot a point. You want to plot a point? Okay, let's do this. Here we go. Out to the left of -4, guys, it's like a table. I need to try. Let's try -5. Out to the left of -4. I wonder what's going out to the left on what's going on to the left of -4. Guys, -5. You go back to the original, replace all these x's by -5, or you put -5 into the factored form. It might be easier to do it here, maybe. So 3 times a -5, help me out, that's a -15. -5 subtract 1, do not let me make a mistake, -6. Down here, -5 plus 4, -1. -5 subtract 3, I think it's a -8. Please tell me, do I have those correct? I did it quickly. That's a positive what, 90 over 8, I think. True? 90 divided by 8 is, what, 11 point something? Is it 11 point something? So that means right here at -5, if I should go up to 11 point something. Is that definitely above that blue horizontal asymptote?
Yes.
So I would think, just based on that, that the graph, the purple, must be up here above, doing something like this, to follow those asymptotes. It's got to be up there. Now, can someone tell me without my testing, does anyone see a way that would assure me that it's up there, even without testing, and not down here? Can Does anyone see anything happening that may say, Professor, I like your testing. You found that point for me, so I know where it's up, it's above that horizontal asymptote, above 3. Does anyone see a reason why it cannot be below?
Is it because it would hit the x-axis?
Go to it again.
Is it because it would hit the x-axis?
Alex, he says, Professor, if you try below, guys don't do this, and follow the asymptote, you're doing this. You follow the red, follow the blue, but if you do that, are you going to end up with an x-intercept? Must it cross the x-intercept, x-axis somewhere? And do we have an x-intercept there? No. We already found the x-intercept, there is none. So it cannot be that. So we're done there. Now, oh boy. Does anyone have an idea what's happening between the two? And by the way, between the two, you got to pick up these 2 points. If not, we may have to plot a few points. Does anyone have an idea what may be happening in between? And so I will definitely do it. Any guesses? What's going on in between? And you got to pick up those x-intercepts. You're going to be shocked what's going on. Hannah.
The parabola
Hey,
facing downward.
thank you. Just wait, Professor. If you got to follow this red and you can't touch it, from left to right, Bishop's got to come up and pick up 0. That true? By the way, at 0, do you think it's going to cross over a little bit and come back down and pick up 1? I think there's a crossover point there. Hannah says she thinks it is, so guys, we do this and make it look a little better here. Give a little bit more curve to it. She said, Professor, I think it's going to do this. And it's going to cross over and do that. Yes or no? And then she thinks it's going to come down now and follow the other vertical, but not touch it. Something like that. Would you guys agree? Now see, some looks like, oh my goodness, I'll be so glad for spring break next week. Oh my goodness, no more Ramsey, no more math2 for a while. Unless I send you something by email to do for me. Yeah, I'm gonna send you a little assignment of some sort. Okay. Guys, you guys agree? Is that possible? Now you can plot points. Now, who has an idea? One more piece. Now I gotta be careful here. It's happening out here. I gotta follow the red, can't touch it. I gotta follow the blue, but I can touch it. In fact, I have the crossover point there marked already. What was it, out 6 of 3? Does anyone have an idea of what that may look like over on the right?
On top of the.
On top, it does not touch that red. Coming down, oh, this marker is almost out. Okay, here goes. Comes down, like that, crosses over. Now when I say cross over, don't get crazy on me. I don't mean this. Why would I not mean that? Because that would come on down and pick up what, another x-intercept? We have no more x-intercept. No, that horizontal is there for a reason. It wants you to hover around, stay close to it. Something like that. That's why it's there. And if I step back and look at it, I hope you guys can see all that. There's my graph. That's my sketch. You see one of these on the exam when you come back from spring break? A good 15 points for one problem. How much is the exam? 80? They're usually 80 points, aren't they? I guess right there's probably a good 15 points right there. And I'm not quite finished with it yet. Guys, are we okay with this? So there can be a crossover. Alexandra.
How do we know that it's a negative graph?
Ah, beautiful. Hannah, tell the class why you thought, I didn't plot points. You can always plot points to make sure. What in your mind gave you the idea it should be an upside down, you described it as upside down parabola.
Because the horizontal asymptote, and there's no crossover point in between the vertical asymptote.
Absolutely. And also, what she just told me here, did you think, Alexander, anyone, did you think it may have done this? Don't do this. And that's your parabola. Is that possible?
It's not allowed to cross.
No, why? If I do it like that and pick up those points, what's wrong? I'm picking up the x-intercepts, that's beautiful. I'm still picking up the x-intercepts like Hannah's purple graph does, but why can it not be this parabola opening up? It crosses over what? The horizontal again, and we already said it just crosses over once. It's out here, 6-3. So I can't cross that horizontal asymptote again. Alexander, did that help?
Yes.
Okay, or you can plot points to make sure. Guys, the graph is done with your help. Time consuming, you have better believe these are time consuming. Now, I've got tons of questions to ask. We have the domain out of the way. Can someone tell me, since I have the graph, suppose you were asked for that? Not domain, range, the up and down. Or can someone in this class maybe tell me, Professor, I think it's not appropriate to ask on this one for a reason. If you consider the up and down. I know it drops down forever, that's negative infinity. That's no problem. How high up does it go? It goes where? Oh, I love that. It goes through infinity? Is this space in here empty?
No.
There's no graph in between.
But we don't know how far up.
Exactly. Hannah's parabola, it goes up to here, doesn't it? Do I know where that point is? No. Could you find that point? No. Mr. Park could. Right, Mr. Park, you could find that point for me, a precise point, couldn't you? Use a little calculus. You have to use calculus. So I'm not going to ask you for the range on that. Absolutely. Oh, you guys, this up here? Whoa, hang on, just 1 second here. Is this one hovering around, what was it, 3 up there?
Yeah.
Is that hovering around 3? So I'm concerned about this point right here. Even though you may say, Professor, will this eventually, right here, since it's going up forever, and it's dropping down a little bit, might it pick up some points that maybe I could consider negative infinity through positive infinity? You guys think it might? Or is it going to just hover around 3? Yeah, it's going to hover around 3. I would not ask you. Range is not that easily seen here. So that's out on this one. Here we go. Let's do some calculus. And we're finished with this. Number 1, I'd like to find the limit as x is approaching 3 from the left of this function. Three, vertical asymptote. Here it is. I want you to stay on the left of it. Now you know your left from your right, so stay on the left of it. So on the left-hand side, I'm talking about this piece here, aren't I? That's the left of 3. Now what is my purple graph doing as it's dropping down and staying close to but not touching that red vertical asymptote? How do you describe this behavior? It's dropping down through negative infinity. Now if I should ask this, limit as x is approaching 3 from the right, which in calculus they will, that means now go to 3 again, but stay on the right. Now you're looking at this piece. This is to the right of 3. And guys, what's that piece doing the closer I get to 3? Positive infinity. Those are my limits. Okay. Now you guys taking Math 7 coming up shortly. I'm not going to do anything like this in Math 2 though. Some of my students in the past have said, Mr. Parker, can you help me out here? He said, Professor, when you say negative infinity, positive infinity, which we need, that's the answer. Aren't you saying there's no limit? When I say infinity, does that sort of translate as saying there's no limit? And I'm using the infinity symbol. Is that true, guys? Mr. Park, aren't there some problems out there if we can find, and there is no limit, and it may not be a negative infinity or a positive infinity? Is that true in calculus?
I
On the
don't,
spot.
I don't get your question. So.
Mr. Mathematician, in calculus, the one who made the highest score on his math, 13 test? I've been bragging on him. Number one. I'm saying, are there some functions in calculus that may, when you find the limit, may come out to be something so odd that you have to say there is no limit. You use the words, no limit. You don't use the infinity symbol for a reason. Can you think of any? I don't put you on the spot.
Some discontinuous functions.
Yeah, something like that. Susan, can you think of one maybe? Oh my goodness. Okay. Now guys, it's tougher. So sometimes you'll find, sometimes you'll say, oh my goodness, I checked the answer, professor, and it says no limit. Actually use the words, no limit.
Piecewise.
And then all of a sudden, maybe, and then another one may be infinity. So what's the difference? So guys, right now we're going to just talk about infinity, negative infinity. Number 3. We got the domain out of the way, we got the limits out of the way. Hang on here. Oh, beautiful, beautiful, beautiful. Here goes. I like to find, I use an R back there. I like to find R of 55. You'll say, Professor, I'll see you during the summer. Because if you ask me to go back and replace these x's by 55, that's what R at 55 means. Go back and replace those x's by 55. Just squaring 55 is a mess. Are you telling me, Professor, you're going to go back and crunch all that business out and see what it's close to? That's what it says to do. Does anyone see something up here that tells you directly the approximate answer? I'm not going to get the exact. When you do go back and replace those x's by 55 back there, Bella says, Professor, I see what it is. Bella, tell the class.
About 3.
About 3. It's close to 3. Why? Is my graph hovering around 3? And I say go out to what, 55? So you're going out to 55 out here, dragging that black graph along with you. Is it getting closer and closer to 3? Now please tell me, Bella, love your answer. Is that approximately 3 for an answer? Is it less than 3? Based on your graph?
Yes.
Is my graph underneath? So will the answer be a little less than 3 because it's underneath 3? So I bet it comes out to be like a 2.9999999 something for the approximation. Mr. Park, as I finish it up, would you do me a favor? Go ahead and replace, I hate to ask you to do this. Replace all these, actually crunch it out with 55
Okay.
in that mess. And see if the answer is close to 2.99. We said it's close to 3.
My computer turns dead.
Huh?
My computer's dead, so I
Hey,
can't.
Susan, can you help me? Just go back to that original, just crunch it out for me until I finish my problem up. And replace all those x's by 55, just crunch it out. And we're thinking the answer should be close to 3, but the graph's close to 3. That's underneath, so it should be like 2.99, way out there. Okay, she'll do that for us. Guys, got that out of the way? What's that?
What number?
Way back here, can you see it?
55?
Yeah, 55,
Okay.
into this function. All right, 55. We think it's close to 3, in fact, it's close to what, 2.99 something. It's underneath there. Number 4, one more item here. I gotta watch my time here, boy. Okay, around the limits, that's beautiful.